And so the kind of algorithm for offsite analysis is to measure out the job site as best as you can. And even if you're using solar design software, you may be switching over to Google Earth because that ruler tool is so handy. But the general design philosophy is you sketch out the rooftop and note all of your shade obstacles, and then you do the rest of the remote site assessment. And that's now kind of the challenge is, okay, so I don't need to get up on the rooftop to do my solar design anymore. Do I have to even visit site to do my solar design, or can I do everything remotely? And what I found is that new construction, you have to do everything remotely because it's not built yet. So the answer is yes, you can do solar design without visiting the site, but you still might need to gather some site data. Taking note of where the electricity enters and leaves the property. This picture here on the left is pretty revealing. What's revealing to me is that we have two conduit sizes. So this is a log cabin, and on the other side of this wall is the service panel. And what we have is an underground utility feed coming up into the meter, and these oversized cables, and then coming out of the meter in this smaller cable. That's what's going in into the residential home, because they wouldn't have like larger conductors going into the residential home than this underground service feed. So now we're going into the home, and if we wanted to do a line side connection, this would be intercepting the conductor run between the meter box and the building main. So our line side connection could go right here, and there's ample room on this wall to mount it. And so we might actually do a supply side connection here, and then go up this wall into a soffit and for our internal wire run. And so what I want to do is I want to take note of the size of this conduit so that I can get my fittings and put a box there. And so during the install, we'll get the utility out to come pull the meter, and then we will pull some of the conductor out through this cable, cut into this conduit here, put in a box, pull the conductors back through into the meter can, and then tap on to the conductors inside this box. So this picture, you want to learn everything about the electrical service you can, where the power enters the property, where it enters the building. All of this data is very useful. Where is your wall mounted stuff around your utility going to go? What this service panel picture tells me is two things. I can zoom in on it and get the rating of this breaker, which turned out to be 200 amps, which is pretty common. And this is a bottom fed, so it's probably coming up from underground into this breaker here. So we get that it's a 200 amp service panel. We can also see if there's space for a line side connection or for a load side connection. It doesn't look like there's space for a load side. And so you have to ask yourself, well, what's the cost of a junction box and a couple of tap connectors? That can be $50, maybe even if it's a metal box, maybe it's $100, versus taking this breaker out here and then putting in a double pole breaker slot with a sub panel, and then reinstalling that breaker, and then putting your solar breakers on the sub panel. If you don't have any space inside your main panel, it may be that a supply side connection is the way to go. And then here we have a commercial control room, and there's a number of code violations in this picture. So what that tells me is even if we have space inside the panel, we still want to consider a line side or supply side connection. So there's a lot of, this is what we have. We have where the power is entering the building. We can go ask, and the thing is, your client has a camera on their cell phone now. So most will be happy to say, you know, if they send you this picture and then you send them instruction to go read the conduit label off of that, all of a sudden you have the conduit size for your supply side tap. You know, they can take a picture of the service panel without opening the panel up and being subject to danger. You know, you have to think about what's going on the side of your building. It could be low impact without microinverters. If you use a string inverter, there's going to be more stuff on the side of your building. You know, do you need to, if you're mounting to siding, do you need to put a board there so that you actually have a straight surface to mount to? It helps to have knowledge of conduit and cables and conductors. The main thing to know when looking at all of this stuff is there's weatherproofing considerations, and then there's physical protection considerations. And if it needs to be physically protected, that's when you start getting into metal conduits. A lot of people say, well, you know, we use EMT conduit because it can be used as a equipment ground conductor. Well, yeah, you can also put an equipment ground conductor in as a cable inside of it, and even if you're using EMT conduit, that's often what you'll do anyway. And so, you know, it's not really that the EMT conduit is providing a ground path. And they say, well, there's this rule that says DC wiring has to be in metal conduit, and that's so that if it arcs, it'll arc onto the conduit and ground out. And it's like, well, wouldn't that mean that like a plastic conduit might be a little bit safer because you don't have this potentially energized metal conduit if there's a problem with your grounding system or something? No, it's, you know, what the metal conduit is for is to prevent a rodent chewing through the conduit and chewing into the cable. And a DC cable can cause fires in that circumstance a little bit easier than AC can, so DC has to be more protected than AC. You know, when you get into emergency backup systems, it might be that you can't use EMT conduit. You might have to use a more rigid conduit, or even a rigid conduit that, you know, you could drive a car into and it wouldn't affect it, depending on how critical the system is. So like metal is used for protection, for physical protection, but then metal by itself, that may be insufficient for the elements. You know, there's indoor applications and outdoor applications. So you have, you know, maybe a metal conduit with no plastic liner, and that could be fine for indoor applications. But if you're going into wet or damp or dry or sunlit environments, you might need to have additional weather protection. So, you know, it starts, in my mind, to simplify when you think, okay, the metal is for physical protection and DC has to be physically protected that way. Plastic is more for being a little bit more weatherproof, and there are combinations of them, like flexible conduit with metal and plastic. But the thing is, that starts to get costly. So, you know, you might use this stuff for little short conduit bends or transitioning from the outdoors into the indoors, and then once you get inside, you might transition into more indoor rated stuff, which is a little bit cheaper, but also a little bit less weatherproof. Collecting whatever building information from the client you can it helps the project go along. You know, I like working in commercial because you often have access to building design documents that you might not get in residential. I was evaluating Half Moon's building a while back, and I looked at this and I said, well, it's a 412 roof pitch, and that's cool. It's 29 gauge steel, okay, but it looks like it looks like they're putting a metal roof on top of horizontal purlins before going onto the rafter, and I hadn't seen that metal rooftop building design before, but they were able to get up into the attic and just snap a picture, and kind of confirm to me what's going on. And I'd say a common attic picture is this, just to confirm what's going into the attic, but you may also want to take a picture of what the truss shape looks like. But then in particular, also hurricane clips. If the truss is secured to the building wall through hurricane clips or not. And why all of this is important is that by the time you get to picking out your racking system, like this is the S5 clamp, and it's telling me, you know, if I'm going into wood decking, wood purlins, or steel purlins. Okay, well, I'm going into wood purlins, and they're going to be 2x4 on vertical, so that's exactly me. You know, number of fasteners, well, there's 3 holes in it, so I'm going to use 3 fasteners anyway. But then what it tells me is that my pull strength going into the purlin is 490 pounds, and my racking software told me that in zone 1 it's not going to be any more than 100 pounds. So, you know, with a safety factor of 2, you know, I'm still well in my safety range to go into the purlins. But this is what I think is very interesting. If this was not metal 29 gauge steel, so it says, okay, you can go into steel, but it has to be at least 16 gauge for those purlins, steel purlins. But this says, what if we used 1/2-inch OSB wood decking? The pull strength was 288 pounds. And that's where I'm saying, look, you know, from a long time ago in our racking software, you know, not all racking companies provide the uplift calculations, but what we can see is that in zone 1 and zone 2, we actually have an uplift of 212 pounds in zone 2 versus 335 in zone 3. And now we're getting into, scroll back down, we're getting into the pull strength of our attachment to the rooftop. And what we see is that the attachment to the rooftop, if we just went into the decking, that we would have enough pull strength for zone 1 and zone 2, but not for zone 3. And so now we see we have a better understanding of why the solar designer does not think that decking-based racking systems can work, is because they can't work on all portions of the rooftop. If you're using a decking-based racking system and you're going to the very corner of the building, you know, you might have a gust of wind come through and pull that module up and out of the rooftop. But if you stick to zone 1 and zone 2, you should be within the right safety factor. So that's, you know, taking the time to go through structural assessment can add more flexibility into what racking system you're going to use. For example, you know, even though it might be decking-based racking systems might be weaker, they also have a less of a footprint. You know, they don't have the heavy rail. In addition to that, they might be railless, and so, you know, they might have more force on them, but they might be overall lighter weight. To kind of finish off our structural engineering discussion, you know, what I do when the client, you know, I try and encourage the client to get engineering stamps on all the projects, but I'm not a professional engineer, structural engineer. I can't stamp structural documents, but I've found even online there are engineering companies specializing in, say, residential structural stamping, where just like the racking companies, you're putting in your snow load, you're putting in your wind speed, you're putting in your array information, but they say, okay, but what lag screw are you using? What's the diameter of the screw? How far deep is that screw going into the building? You know, are the standoffs staggered? What's the standoff spacing? What does the rafter look like? All of this stuff is necessary for a professional engineering stamp. What's the ceiling material made out of? What's the slope of the roof? How, you know, the stuff that we see from the racking design. So what I've tried to do is they're included in the program, but what we can see is after you do your array layout, and while the customer is kind of walking around their building taking some pictures, the more you can plan up front in the design phase, like which exact lag screw are we using. Normally that decision might be made by the installer on his way to site. Oh, we need some lag screws, got to go to Home Depot. But if you pick up on all that stuff beforehand in the design phase, then you might be able to find engineers online. The cost of stamps from this particular company gets down to below $500 a stamp if you're giving them regular business each week. So, you know, it's if you can provide a structural engineering stamp to your client for $500 and no other solar installer is doing that, you know, you just look a lot more professional than the others. And you know, engineers will be assessing the roof truss for the additional load put on by the solar array, taking the effects of wind and snow into account. Okay, so let's what we're going to do next is walk through you know, kind of example in helioscope and an example in solar design tool, and then we'll use the remaining time in class to answer any questions, maybe pull up some of the software and do it in front of you live. But with in the meantime, I've made screenshots to make the presentation go more smoothly. And what I want to show here is not necessarily how to use the software, but that once you know one solar design software, the interfaces on others follow similar algorithms. You know, you put in your job site, and then you know, sometimes it's easier to start with putting the clearances in first, because if you say, okay, I'm going to have my solar array cover this entire area, and then you try to click on that area to put in a keep out, you might select the whole area and not just where you want to select. So I like starting with modeling where the modules aren't going to go, and so we have our 3 feet off the sides, 3 feet off the top, 3 feet off the sides, and then here we have some other kinds of obstacles. These are plumbing vents, and on, you know, with vents, you know, you can use that product we showed where you reroute the plumbing vent. My preference, and on a roof like this, I probably would use that product, but my preference is to follow commercial guidance and stay 4 feet away from roof-mounted obstacles. That's just been my experience with roof leaks. It's that the pre-existing, you know, to a trained solar eye, we can decipher these little smudges as plumbing vents. And you know, what I like doing is I like leaving a couple of rafters on either side in between those plumbing vents, so that you know, the installers may not walk around them, and B, you know, the solar array isn't kind of wiggling the roof decking right around where that plumbing vent is. Maybe that's too you know, much of a concern of mine. The real problem that I find is that even if you're blocking 4 feet on each side from the plumbing vent, you know, if you're putting modules in this area and now your rooftop is a construction site, all of a sudden your keep outs and offsets become walkways. And so actually not going all the way up to the plumbing vent but stopping 4 feet short can produce its own set of problems, because it might be actually encouraging people to walk right next to it during the project site rather than otherwise. So you need to talk with your installer about those issues before you get going. But anyway, with residential, it's 3 feet off the sides, 3 feet off the top. With commercial, it's 6 feet off the sides. Every 150 feet, you need an 8-foot wide walkway. There's a little bit of flexibility on that. And then stay 4 feet away from roof-mounted obstacles like air conditioning units. So you model where the solar array can't go. You know, there's the difference between staying 3 feet off the sides. So here we're saying say 4 feet off the sides or whatever with no setback. But here we have our obstacle, and we're giving it an actual 4-foot setback to stay 4 feet away from everything. So the air conditioning units are modeled a little bit differently than just the plain, this is a no zone. So it's does your restriction have an offset or not? Then you get into shade modeling. See in this picture is that we've clicked around the entire tree, and then what might not be so apparent is that we've assigned that tree a height, and now we can see the shadow of the tree resulting from its height. And then we have a window frame to say, well, when do we really want to apply the shadow? Because in the winter time, we can go back to our PV watts estimate, and our PV watts estimate says, hey, the array is not turning on until 9 o'clock in the winter time. And so maybe we analyze our shadows for, and what's very common is to go and do your shade analysis on winter solstice between 9 a.m. and 3 p.m. And that'll take care of your worst case scenario north-south shading. But also you have to remember is that shadows don't just run north to south. Shadows run east to west. Shadows go north. In the shadows also go south. In the summertime, the sun rises in the north part of the sky. And you look and your shadows face in the other direction. It's facing south, even though we're in the northern hemisphere and our shadows should be running off north. So shadows move around, and that you definitely want to check winter solstice, but it might not hurt to also check, spring equinox and fall equinox, and maybe halfway in between, just to make sure you've considered all shading scenarios. And that's actually changing, that thought process is changing the way shade analysis works, and we're going to get into that in a minute. So we've said where the array is not going to go. Now we're adding a segment that shows where the array is going to go. And in the videos I've made on this, I actually made a mistake. Because what I did, I was thinking, okay, well, I'm on the south side of the roof. I want the modules to go all the way along the south side of the rooftop. And then you'll see in the video, I had problems aligning the modules on that surface area. What I should have done is, given that I have these keep outs here, I should have done, okay, I'm going to do one section here and another section here and another section here, so that so it didn't have to be, there's no reason that the grid going across this way be all matched up. And what you'll see is I ran into a problem that if I shift the array that way, I lost a few modules here, and if I shift the array the other way, I lose a few modules there. And that was because the whole roof surface is shifting over and not just the individual subsection. So you have to, there is a slight learning curve to these softwares on the best way to model this stuff. But anyway, after we choose where our field segment's going to go, we're entering our solar module. And so these softwares, just like your manufacturing softwares, have the modules already built into them. If you right-click, you have a couple of options. You can remove an individual module from the array. Also, what is a very useful section is you just right-click anywhere and you say align modules to click, and it'll line up with where you're clicking. I said shade analysis was changing a little bit. The way now, so kind of the pencil and paper way would be to do a shade analysis on winter solstice. But now that you have data for every single hour of the day, every single day of the year, instead of doing shade analysis based on winter solstice, you can do shade analysis based on total, production out of the individual module. So on this particular job site, remember, we have a tree at the edge of the property. And what we can see is if we don't cut down the tree, it's actually kind of ironic, but the modules on the northeast side of the home that are further away from the tree actually produce more energy than the modules that are on the southwest side of the rooftop right next to the tree. And so if we are not concerned at all about array aesthetics, but we're only concerned about raw power, but the client doesn't want to cut down the tree, what we might find out of the design process is that the best array is the one that is on, this half, the half of the building that is furthest away from the tree. And so what I might do here is just chop off that section, perhaps even, and chop off this module here and do this array on that side and that array on the other, and not have shading issues because we're avoiding the modules that are most impacted by shade. And so you can evaluate the modules to see what, and it might be surprising. You might find that the solar panel that is just directly east or just directly west of the air conditioning unit actually gets more shade than the one that is located directly north of the unit. And then once your array layout is complete, Helioscope has an electrical section where you in addition to establishing array zones, you establish electrical zones, and it just based on the inverter you've selected and based on the module you've selected, it automatically generates the string sizing and wire runs, which are then used to calculate voltage drop and energy estimates. And you can, what's nice about this is here what we're doing is instead of just getting our data from one PV watts weather station, we're getting it from two. And so you actually might pull in weather data sets from 4 or 5 different nearby PV watts weather stations and then average them together to kind of get a better understanding of the overall environmental conditions of the surrounding area. You can copy your projects and experiment with different modules, different inverter types, and different tilt angles, and even things like with PV watts and snowfall. So with PV watts and snowfall, it's just a percentage. It's, okay, we've calculated 0 or 5, which means we've basically just taken 5% of the production off the top for the entire year because we assume there's going to be snow on the array. Well, in a more advanced software like Helioscope, you can go in and put it in specifically for December and say, instead of losing 5% of the year, what does it look like if we lose half of December? And that might be a little bit more accurate model. Solar Design Tool is more of a software that's used after you've done your shade analysis. So Helioscope does shade analysis. It might not be quite as fancy as Aurora's, but they do have LiDAR data. But their approach is they build a 3D model, but their default view is a 2-dimensional view. And that's because they're more perhaps applicable to large commercial job sites, large utility scale job sites where a bird's eye view is really all you need. But they are building an actual 3D model, and by assigning heights to the objects, they're using trigonometry for the shade analysis. Solar Design Tool doesn't do shade analysis. It's really more for permitting and documentation. And but the array layout is the same. You know, you're defining your roof area by tracing over a Google Maps image. You know, you may not, you don't have that LiDAR data. You may need to guess at the roof type, but you know, to be perfectly honest, there's not that much dimensional difference between a 412 roof and a 512 roof. You know, so that if you're close enough and you're leaving those offset distances anyway, then you're really not in that much trouble if you are off by one roof tilt angle size. You know, you point which way the module is facing. You know, here we've added restrictions on where the modules are or aren't going to go, similar to those keep outs with helioscope. And so the reason why I'm putting this on here is simply to show you that the array layout for one software is a similar process to the other. Now with Solar Design Tool, it's more finicky. You know, after we do our preliminary model, we can see that our rooftop really isn't straight. And so you have to right click and then edit the boundaries. And some of it's not a true CAD environment. Some of these boundaries you can't just click on and change the value. You have to kind of wrestle with it for a while. So that's a little bit of a problem with Solar Design Tool, is that it's not quite as user friendly as the. It's also it's one of the cheaper ones too, so we can forgive it for being a little bit less user friendly. We're in Solar Design Tool, and now you can see Solar Design Tool has a setback section where we go and model the setbacks separately, and we can say don't go on the eave, but go on the valley and the ridge and the rake. And now it auto fills in the module based on what module we've selected, and they even now do racking, where you select your module and your racking system, and it spaces the modules out appropriately. Inverters too. You know, with an inverter, there's really not much sizing to be done with an inverter. It's, hey, is the inverter compatible with the solar module or not? And generally that comes down to whether it's a thin film module or a 60 cell module or a 72 cell module. It's unusual to have a 60 cell microinverter not work with a 60 cell solar module. But I want to show you a microinverter spec sheet. You remember, your manufacturers want to make it as easy as possible for you to design a system using their products. There's a microinverter spec sheet, and here's output data for the microinverter. And here we are on 240 volt electrical service, and under output data, it says the nominal output current is 0.9 amps on 240 volts. And it says the maximum units per 20 amp branch circuit is 17. And so what this spec sheet is saying is that you can have up to 17 of these in-phase microinverters on a 20 amp branch circuit. And the electricians in the room are saying, aha, 0.9 amps times 17, that's going to give you about 15.6 amps. And then when you upsize that by 25% and then round up to the nearest breaker size, you get a 20 amp breaker. And so in-phase is limiting, and you can get all this data, and you know how to read the spec sheet. You go into your design software, and now does it for you. So here we have two different surfaces, the north side of the roof, the south side of the roof. The south side of the roof is smaller than the north side of the roof. The north side of the roof, we're doing 17 modules across. And if we fit 18 modules across instead of 17, I would probably not do the extra modules. keep it optimized for this particular system. 17 modules across on the northeast section, and then on the southwest section, we're going to do that one middle section of 8 modules, and then the 2 side sections of 6 modules on a shared circuit. So we'd have to build a jumper cable for the first branch circuit, and then what we have now total is that we have 4 branch circuits of different lengths for this apartment complex. So it's very similar to string sizing software at that point, except we've also done an array layout. And remember, your array layout is a function of your spec sheet. Your string sizing is a function of the spec sheet. There's no reason why this stuff can't all be automated. Now, this is what I think is very, very interesting about Solar Design Tool. So with Helioscope, once you get to the electrical wiring, it's going to propose some wiring configurations, and you're going to be able to change the wire sizes and see its impact on system performance. But that's more for modeling. But with Solar Design Tool, not only can you once you've done your array layout and you've determined your string sizing, then you can go back in, and while it takes some time to figure out exactly where in Solar Design Tool to go to do this, you can go back into Solar Design Tool and rearrange the modules. So maybe it started out that it put all of circuit 1 going across the top and all of circuit 2 going across the bottom. Well, you can drag and drop these modules on and off the roof, and we have to go and put that one back there. But you can rearrange the modules so that circuit 1 is all over here and all over here, and circuit 2 is in the middle instead of going across. And then, to my knowledge, the Solar Design Tool is the only software that does this, and it's a very useful construction document to tell a general contractor what modules are going on which circuit, and it's still incomplete, because it's not telling you where the circuits start and where the circuits stop. But it goes much further into construction documentation than the others. So after you model your array out in Solar Design Tool, you can go back and re-edit the module inverter configuration, but then a new option pops up that'll say specify balance of system components, and when you're done with that, a new pop-up will occur that says change your conductor and conduit sizes, and you'll get report lists. So it kind of coaches you through the process. You're still going to have to decide if you want to do a load side or supply side interconnection. Here in Solar Design Tool is where we're choosing between a load side and a supply side interconnection. We're choosing between having a breaker box like you might do to combine multiple branch circuits, or a fused disconnect, which you might do if you just have a single inverter on your property. So it asks some other questions too. Do you want an AC combiner box? Do you want a production meter? It kind of takes you through the survey. How are you going to be grounding the array? And again, this is a great tutoring tool, because if you don't know the answers to this, you can't continue. So it forces you to go and research what you don't know. And then it's all integrated so that when we say, okay, I want a supply side connection with a breaker box and a production meter, then on the one-line diagram, what pops up is the breaker box, the production meter, and then this is the supply side connection where we go off to the main or go off to the utilities. So filling out this survey impacts the automated one-line diagram creator. We have to put in our conductor types, which are generally just based to the weather rating and voltage rating, and it's always fine to use robust cable in the solar industry. Put in your voltage drop. This this survey part, you might say, well, this is starting to get beyond performance estimating and into construction. It's like, yeah, that's the point, is to show you you don't need to spend weeks putting together a construction document. It's just saying, okay, are the conductors above the roof? How far above the roof? Because now you have to do temperature correction if the conduit is less than ½ inch above the rooftop. What you're doing in this screen is putting in all the information about your wire runs. And all of the results are exportable to CAD. So if you're putting in a specialty device, if there's something unusual about your project and you can't quite model it, you can make adjustments externally in CAD. This is where we're going to Google Earth, and we're going back to our drawing, and we're starting to kind of measure out the lengths of our wire runs. And then later, you can go in and re-edit your balance of system components and change the conductor and conduit sizing. And so, if all of your conduit and conductors are various sizes, here is a 75-inch diameter conduit, a 1/4-inch diameter conduit, 3/4 inch diameter, a ½ inch diameter, 3/4, 3/4, 3/4. Okay, so what's going on with that ½ inch? Why is it unusual? Well, remember, our circuits on our roof are different sizes. We have a circuit of 17, a circuit of 17, a circuit of 8, and a circuit of 6. This circuit of 6 is using number 12 conductor, and that's smaller, so it really only needs to be in a ½ inch diameter flex steel. But a construction manager might look at this and say, all right, well, we're not going to use a spool of 12 and a spool of 10. We're just going to use a spool of 10. So we're going to change that to number 10, and we're going to change that to number 10, and this is going to number 10. And Solar Design Tool will update the conduit in real time, but then you might go and make sure this is 0.75. And it'll adjust things like the voltage drop in real time, so you'll be able to see the impact of your decision on the design. But this is what I'm saying is, like, it's a learning tool. It's also a work tool. An amateur will do this and then go out and buy a whole bunch of different wire sizes. A pro will take a step back and say, no, it's okay for me to upsize my wire. I'm going to keep my fittings and connectors and conduit sizes and wire sizes as uniform as I possibly can. It also shows an inspector that you've gone through and calculated your conductor fill for every single conduit run on the project, which gives them much more confidence in you if they've never heard of you before. And to follow the rest of this, what it calculates, the breaker size, the temperature rating of the terminal that the conductor is landing on, temperature correction, conduit fill correction because of conduit fill. All of your major National Electric Code calculations are picked up in this report, including voltage drop. And then, of course, the end result is a one-line diagram. So here's our 2 microinverter circuits of 17 per circuit, and then our 8 per circuit, and our 12 per circuit. I didn't go in and put those numbers into that. This is all automatically generated.